Hello, good day. In this video, we'll be looking at Leibniz's formula, also called Leibniz's rule. Please note that the original file that I had uploaded for this had a issue with the link. The link, which is what I had used last year, was no longer working, so I had to update this link, and this is now the correct link. This gives you some basic information on Leibniz's formula as well as some examples with solutions. Now, when we are talking about Leibniz's formula, in this discussion, we'll be using this notation. So everyone knows that the nth derivative of, let's say, y with respect to x can be written using this notation. We will also be at times using this notation, which is d to the power of n to represent the nth derivative of whatever is inside here. Alright, so if I wanted the first derivative, I would put d to the power 1, second derivative, d to the power 2, and so on. Okay, so why do we need to use Leibniz's formula? As you would remember, as we discussed in the last class, if I want to get a high order derivative, let's say second, third, fourth derivative, etc., what I could do is start from the original function. In this case, I'm looking at a product uv, and I could differentiate that as many times as I need. Right, so if I wanted the first derivative, I could simply use the product rule and get my derivative. If I wanted the second derivative, then I take the first derivative and I differentiate again. And after you simplify, you would get something of this form. And we can continue doing that. So in each iteration, we go back to the previous one and differentiate that one time to get the new one. And if I wanted to, let's say, find up to the fifth derivative, then I could use this approach. So I get the first, second, third, fourth, fifth. Now this takes quite some time, right? Because these are just the simplifications that I've written down there. There is some work involved in going from one step to the next before you could get to this simplified form. And because of that, you wouldn't really want to use this if you have a question where you want to work out a higher order derivative. So in a case like that, we would rely on Leibniz's formula. Now, before we actually talk about what the formula is, I just want you to pay attention to something here. So notice there's a pattern. If you pay close enough attention, you can see a pattern developing here. For the first derivative, the coefficients are 1. Right, so let's look at the coefficients first. For the second derivative, the coefficients are 1, 2, 1. Third derivative, 1, 3, 3, 1. Fourth derivative, 1, 4, 6, 4, 1. Fifth derivative, 1, 5, 10, 10, 5, 1. And this goes on. If you wanted the sixth derivative, the coefficients would be 1, 6, 15, 20, 15, 6, 1. And you might ask, well, how did I get those values? And the answer is that these values, the coefficients that I just called out, these are all the values appearing in Pascal's triangle. Right? If you are familiar with Pascal's triangle, then you can use that to get your coefficients. If not, we will discuss that. We will discuss how we get it in a little bit. But those are the coefficients. The second thing is, notice that in each of these equations, in each row, if you want to consider it a row, the first term has u, right? In all of them, the first term has u. The second term has u prime, right? U prime. The third term, well, there's no third term in this one, but the third term has u double prime, right? And we keep going like that. So the fourth term would, if there is a fourth term, it would have u triple prime, and so on. And it's the reverse for v. The last term has v, second to last term has v prime, and then if there's a third to last term, it would have v double prime, and so on. So what you'd note, another thing you could notice is, so we have u v prime, u prime v. Notice that if I were to add up the number of times I differentiated in this term, this wasn't differentiated, this was differentiated once. Same thing here, 1. So each term is has a total derivative, you could think of it as 1. total number of times differentiating. In this here where we have the second derivative, right, total number of times we differentiated is 2. Here we did it once and once, so again the total is 2. Same thing here. And third derivative, fourth derivative, etc., the same pattern follows. So if when you get to the fifth derivative, total number of times differentiated here is 5, then 1 plus 4 is 5, 2 plus 3 is 5, and so on. So these are all patterns that we could use to, well, if we were to generalize this, that is what we would get from Leibniz's formula. Okay, so let's look at what the formula actually says. So it says given two functions u and v, the nth derivative of the product uv is given here. Alright, so again we're using this notation. D to the power of n represents the nth derivative. U of x, v of x is the product. What the formula says is that it's equal to a summation. Notice that here it's always things being added. Right? So once we have things being added, we can represent that as a summation. So it's a summation. K goes from 0 to n. We have this term here which is n choose k. Right? This, I hope you all remember what this means. And then we have a product here of derivatives. So we have the kth derivative of u times the n minus k derivative of v. Right? It might look a little confusing. You might not be at the first glance be able to interpret this very well, but if you take a minute, look at it, compare it to what we have up here, you'll see it kind of follows. So like I said, I already said it's a summation, right? And then the first term is n choose k. Remember the first term, or the coefficient is n choose k. Remember up here when we're talking about the coefficients, we are referred to Pascal's triangle. The terms in Pascal's triangle are of the form n choose k. N represents the row number, or in other words, the number of times we're differentiating in this case. And k represents the number of terms that we're looking at, or the term number. So if we're looking at the first term, actually, if we're looking at the first term, we would take k as 0. So k is 0 here, then 1, then 2. Remember, n is the number of times differentiating, so it always goes from 0 to n. So 0, 1, 0, 1, 2, 0, 1, 2, 3, 0, 1, 2, 3, 4, etc. So that's why we have to start at 0 and end at n, well, to get the terms that we want in Pascal's triangle. So n choose k will give us that. And then remember here, we said we start with u, and then we keep differentiating increasingly the number of times, we increase the number of times we differentiate in u. So we start with u, then we have first derivative, second derivative, third derivative, and so on. So remember, k goes from 0 to n, so we start with the 0th derivative of k, then the first, then the second, etc. So that's how we get this. As k increases by 1 each time, we'll get the terms we need. Now for v, we did it in the reverse direction, or the reverse order. We start with the highest possible power of, highest possible derivative of v. Remember, this is our first derivative. We want highest possible derivative we can get is v is our first derivative, and then we get one less, which is a 0th derivative. If I skip and come down here to the 5th derivative, the highest possible derivative we can get for v is a 5th derivative. So that's what we start with. Then we go down from there. So from a 5th, we go to a 4th, then a 3rd, 2nd, 1st, and then 0. Right? And how we represent that is by taking the n minus k derivative. So when k is 0, we get nth derivative, which is the highest. As k increases, this will decrease by 1 each time. And again, notice when I add k to n minus k, right? If you add the number of times you're differentiating, the k is cancelled and we just get n, which is what we saw before as well. Right, so here this is what the formula says, where n is a positive integer and x is any value that is in the domain of both functions u and v. Alright, so this looks a little complicated, but it will be much more straightforward once we try to use it. In case you didn't know what n choose k is, it's represented by this formula here. You can easily get this from your calculator if you're not sure how to work it out. Alright, so it's n factorial over k factorial by n minus k factorial. Now, these are some easy ones that you are supposed to know or you should know, and they will greatly help you simplify your working. So this first term here, notice the first term is always 1, right? Coefficient, which is the same as n choose 0. And also the last coefficient is also 1, which is that coefficient represents n choose n. So that's how we get these two, this one here, n choose 0 and n choose n. Both of them are 1. Again, you could try it using the formula or a calculator. You will see that regardless of what n is, this is always true. Now, these two, n choose 1 and n choose n minus 1, what are those? Well, n choose 1 represents the coefficient of the second term. Remember, the first term corresponds to k is 0. So n choose 1 represents the second term. So remember, for the second term, well, we'll ignore this one because this only has two terms. For the second term here, the coefficient is 2, then 3, then 4, then 5, which is the same as n. Right? And also, same thing for the second to last term. 2, 3, 4, 5. Right, so that's what we noted here. N choose 1 and n choose n minus 1 are both n. Now again, you can easily get this if you substitute k is equal to 1 into this formula. 1 factorial is 1. N factorial over n minus 1 factorial is just everything cancels except the n in the numerator. Right? When you expand it out, everything down here will cancel with everything except a single n. And same thing for this one. Also, in general, this is true. You don't really need to pay too much attention to this. Right? Also, the zero derivative, we just define the zero derivative as the original function just for the purposes of using this notation. Okay, so using this, we can expand this formula into a much more user-friendly form, something we can easily look at and relate to. So what we're going to do is expand the summation. We're going to get rid of this summation, sorry. So what we do is we take increase in values of k from 0. So we can write the coefficients first. So we have n choose 0, n choose 1, n choose 2, etc. up to n choose k. And then we keep going. This is some general k in between. And then we have second to last term, n choose n minus 1, n choose n. So we write out the coefficients first. And then we look at what are we multiplying those by. So remember I said you always start off with u because k is 0 here, right? So you start off with u and then you increase the number of times you differentiate u. So u prime, then we would have u double prime, etc. up to the n minus 1 derivative and lastly the nth derivative. Right? It always ends at the highest possible derivative, which is given in this expression on the left hand side. And remember v, we said we go in the reverse direction. So we start differentiating the maximum number of times, n times, and then we differentiate one fewer time as we go. So this here is our expanded form of Leibniz's formula, and this is easier to remember and is easier to use. Again, pay attention to what you're multiplying. Every term here has three things. It has a coefficient, which is just starts at whatever n is, choose 0, and then you increase from there until you get to n. Right? The top term is always n, and the bottom one is 0, 1, 2, 3, etc. up until n. So that's the first out of the three things. The second thing is the derivatives of u. You start with u, and then you increase the number of times you differentiate as you go. And then the third thing is the derivatives of v. You start with the highest derivative and then you decrease that one as you go. And that is what you will get when you use Leibniz's formula. Alright, using these things that I mentioned here, we can simplify Leibniz's formula. The first two and the last two terms, you can simplify those. This coefficient is 1, this coefficient is n. This is a general term, so we can ignore that for now. This coefficient here is n as well, and this last one is 1. Alright, so this here is your Leibniz's formula. Okay, let's see how we use this in practice. So suppose I asked you to find the third derivative of this product, x to the power 5, 1 plus x to the power 4. Well, you could expand this, but that will be a lot of work. So let's, just for the sake of explanation purposes, let's see if you can use Leibniz's formula. Now, typically, it does not matter what you let u be and what you let v be, right? But I usually just let u be the first one and v be the second one. Or, this is sometimes useful if there's a x to the power of some power, like if there's some power of x in the product, I would always let that be u. And I'll explain why when we get to the second example. So we'll let u be x to the power 5, and this term here is going to be v. Now the first thing I usually do is write down the derivatives, right? And I like to write them like this, and I'll explain why. So remember, we're going to need up to third derivative for both of them. So we start with u, we start with v, and we differentiate and see what we get. U prime, u double prime, u triple prime. V prime, v double prime, v triple prime. Okay, so let's state Leibniz's formula and see if we can use these now. Now, Leibniz's formula, when n is 3, right? In this case, n is 3, so we could take this and substitute n is 3. Remember, the coefficients will be n choose 0, starting with n choose 0. So 3 choose 0, 3 choose 1, 3 choose 2, 3 choose 3. And then we have u prime, u double prime, u triple prime, and then in the reverse direction, v triple prime, v double prime, v prime, and v. Right? Notice this is really easy to remember if you try to do it this way. Right? It's not too difficult if you follow that trick. Then we can simplify the coefficients. So remember, this is 1, this is 1, this will be 3, and this will also be 3. So the coefficients are 1, 3, 3, 1. After that, we can substitute our expressions for the derivatives. So this comes to why I like to write it like this. Notice the first term is u v triple prime. U v triple prime. So you take the last one and multiply it by, the first one in u and multiply by the last one in the v column. Alright, so it goes this way. And then the second one is u prime times v double prime. So this one, then this way, and then that way. So you can easily pair them off in opposing directions. Alright, that'll make it easier to remember what you're multiplying. Alright, so we have this. Now I'm going to leave this for you all to simplify and show that it works out to be this thing here. Again, just because this is just for explanation purposes, I'm not going to simplify this any further. I'll just leave it as it is. Right? I'm not going to multiply this out. Alright, so second example. So like I said, whenever there's so we have a fifth derivative here, x squared cos of x. Whenever there's a power of x, I will let that be u. So let u be x squared and let v be cos of x. So again, we write down our derivatives. So for u, we get 2x and then 2. And then notice what happens after this. When you differentiate a constant, you get 0. So everything after is 0. For v, you have to be careful. Cosine, when you differentiate that, it repeats eventually. So for cos, you'll get minus sine, then minus cos, and then it goes back to sine and cos again. So every fourth time you differentiate, you get the same thing. You get back what you started with. Right, and then this also repeats from there. That's just something that might be useful. Alright, so again, you write down Leibniz's formula. We have our coefficients, 5 choose 0, 5 choose 1, etc. And then we have u prime, u double prime, etc. Fifth derivative of v going down. Right, remember it's a fifth derivative we want. So we simplify the coefficients. Now you can simplify the coefficients and substitute at the same time. I just did it in separate steps just to avoid any confusion. So the coefficients are 1, 5, 10, 10, 5, 1. And then we substitute now. Alright, now this is why I said I usually let u be the power of x. Notice what happens here. There's zeros here. So when I'm gonna multiply these terms, right? I'll have the first term, right? That's fine. X squared times this, 2x times that. Second term is fine. Third term is fine. But from the fourth term onwards, I'm just gonna get zero because zero times this is zero. Zero times that is also zero. That is also zero. And if there were more terms, again, I would get zero. So in practice, when you're actually substituting things into here, it's only the first, because I have three non-zero ones here, it's only the first three you'll actually have to work out. The others will just be zero. So we substitute into the first three, the others are zero, and then we simplify it, and this is what we get here. All right, this is our final answer. Notice if you wanted to differentiate this the long way by differentiating this thing once, then twice, etc., that would take a really long time before you could get to this. But with Leibniz's formula, we could easily get that in, well, after you work out the derivatives, you can get it in one. Like I said, you could skip this and go straight from this to this step, and then final answer. So it's much more straightforward. All right, another example here, x cubed ln of x, and we want the fourth derivative. So again, we let u be x cubed, we let v be ln, and we write out our derivatives up to the fourth derivative. All right, we have a 0 here, which means that the last term will be 0, so I don't need to actually plug in the last one. I just need to work out the others. So again, we use Leibniz's formula, write down our coefficients, write down everything else in the products, and then substitute. All right, notice I skipped the intermediate step here and I just substituted everything at the same time. All right, the coefficients are 1, 4, 6, 4, 1, and then we plug in those things from the table and simplify. All right, now in this case, notice here, everything just simplifies to 6 over x. Right? Make sure you simplify it as much as possible. Do not leave it like this because that can be simplified. All right, this is really nice. So we have a derivative of this thing involving ln by something that just works out to be 6 over x. All right, one final example on this here. X squared e to the power of x. I'm going to leave this for you all to look at yourselves, but again, it's the same thing as before. Just note that for v, whenever you differentiate, you get the exact same function. Right? So it doesn't matter how many times you differentiate that. When we simplify, we get this expression down here. Now, because of this thing, this observation here, that whenever we differentiate v, we get the exact same thing, and because we know that from the third derivative onwards this is 0, we could actually generalize the nth derivative of this product. Rather than just the third derivative, we could have generalized any nth derivative for n greater than or equal to 3. Right? So this is just saying what I mentioned there. So for n greater than or equal to 3, if we leave n, don't plug in 3, right? Just leave n and see what we get. Remember, we are only going to get the first 3 terms because everything after will be 0. So we just have to write the first 3 terms and we could write plus 0 after that. Now n choose 0 is 1, n choose 1 is n. Now n choose 2 is not one I had stated before, but this can sometimes be useful to know. N choose 2 works out to be n times n minus 1 over 2. Right? And again, you can get that from the formula if you weren't sure. Once you cancel everything that you can cancel, you will get this, n times n minus 1 over 2. Alright, and then we plug in what u is, what the derivatives of u and the derivatives of v. So remember, the derivatives of v are just e to the x. So it's really the derivatives of u we need to pay close attention to, x squared, 2x, and 2. And we can simplify that, and this is our expression here. So if we wanted, let's say, the 10th derivative of this thing, we could just substitute n as 10, and we get our answer. Alright, really straightforward. Alright, so one last thing you need to know about Leibniz's formula is how to use it in differential equations. Now, a differential equation is just an equation involving derivatives. So let's see what we can do with that. Consider this equation here. 1 minus x times y is equal to x squared. Y is some function of x. Now, I could have rewritten this as y is equal to x squared over 1 minus x, right? but I'll just leave it like this to avoid any fractions. Suppose I wanted to differentiate this entire equation. Right? I could differentiate this entire equation. The left hand side, well, the right hand side is easy because x squared just becomes 2x. And on the left hand side, if I wanted, I could use product rule, right? 1 minus x times y prime, plus minus 1 times y, so minus y. And because this equation has a derivative, we would call this a differential equation. If I wanted to, I could continue going. I could differentiate this equation again, right? And then simplify it. And this is what I get. Now I have a second derivative and a first derivative. I could, if I wanted to differentiate again, then this 2 becomes 0. And, well, after I simplify this, the rest of it, I can get this equation. Notice that no matter how many times I differentiate this equation again, I will always get 0 on the right hand side. Right? Also, if you compare the equations, compare this equation to this equation. Well, not so much this one because this has a 2. Notice here, right? Whatever the derivative of whatever the highest derivative is, y to the derivative of y, fourth derivative of y, that is also the coefficient of this other term. So third derivative, there's a 3 here. Fourth derivative, there's a 4 here. And also this is one derivative. The derivative here is one fewer than this. Same thing here. So you can see a pattern developing, right? So it looks like if you were to differentiate the equation n times, as many times as you need, then for n greater than or equal to 3, this equation is true, as long as y satisfies the original equation. Right? It looks like this is true. Right? The reason why we start at 3 is because, remember, we want this to not have a non-zero number, so we need to differentiate at least 3 times. Alright, so we think that this pattern is correct, right? Now you can't just do that. You can't just differentiate a couple times and say, well, okay, this is true. That's not how a proof works. This is just establishing what the pattern is to yourself, and then you actually have to verify, well, not verify, but you actually have to prove this rigorously. And how we would prove it rigorously is by using Leibniz's formula. So we take the original equation, right? Well, yeah, we take the original equation and we differentiate n times with respect to x on both sides. Now, if n is greater than or equal to 3, then on the right-hand side, we get 0. So we're left with this, the nth derivative of this product. Now, using Leibniz's formula, I could work this out. Right? Whatever the unknown thing is, you should let that be v. Right? So y is unknown, so you should let that be v, meaning this 1 minus x has to be u. So, using Leibniz's formula, we would have, remember this is the equation we're using, right? So all we're going to do is use Leibniz's formula on the left-hand side, replace this with the definition, well, the formula we got from Leibniz's formula, and equate it to 0 because it's equal to 0. So this is remember it's the summation, k goes from 0 to n, and choose k, the kth derivative of 1 minus x, which is u, times the n minus k derivative of v, which is y. Right, I'm using this notation now because this is the notation I'll use going forward. I just use the d notation just to simplify the explanation. Now 1 minus x. When I differentiate that once, I'll get minus 1. But when I differentiate it twice, or 3 times, or 4 times, I'll always get 0. So it's only the first 2 terms I need to consider. Right, when I have k is 0, which is, this will just give me 1 minus x. And when k is 1, this will give me minus 1. So from k is 2 onwards, we just ignore it. It's 0. So rather than leaving it like this, it'll be helpful if I could expand the summation, because then I could just substitute 0. Alright, these terms are 0. So we have the first term, k is 0. Second term, k is 1. And then everything else. Now the first term, you don't actually have to write it like this. Right? When you're expanding this, you could simply just go straight to this step. I just wrote this out again to explain to you all exactly how it is we got this. All right, but when k is 0, we know the coefficient is 1. This is just going to become u, which is 1 minus x. And this is the highest derivative possible, which is nth derivative of y. The second term, we know the coefficient is n. We know this, when we differentiate this, we get minus 1, and this will be 1 fewer than this, the number times we differentiated. So it's a n minus 1 derivative. All right, now I could leave it in this notation, or I mean, this is a lot to write if you think about it, if you're going to be writing this a lot. So it's much nicer if you use this notation. So I like to use this sometimes. So nth derivative of y and n minus 1 derivative of y. Notice the brackets. You have to use the brackets here if you're using this notation. Right, and this is the equation here that we had suspected was true up here. So now we formally proved it using Leibniz's formula. Another thing that you might sometimes see is you might be asked to prove something like this, but for a specific value of x. For example, suppose I took x as 0 and I plugged it into this equation. Right? Then 1 minus 0 is 1. Now this y, remember y is a function of x. So this derivative has to be at the point 0. So you would represent that like this. This is the nth derivative of y at the point 0. Similarly, this is the n minus 1 derivative of y at the point 0. That's just something that is important to note because you will sometimes see things like this. Alright, so let's see how we actually use this in a question, in an example. So let y be a function that satisfies this differential equation. Now we have two products here, not just one. We want to show that this equation is true for all integers n greater than or equal to 0. Now because the right hand side is already 0, then once we differentiate, well, I mean, we can just plug in the values at the start, or we can differentiate as many times as we want, and it's always going to be true. Notice here though, this is at the point 0 when x is 0. Everything is at the point x is 0. Alright, so this question actually has two steps. The first step is to use Leibniz's formula to get the general nth derivative of this equation. And then once we do that, then we have to substitute x is equal to 0. Alright, so first, so this is why I said first we'll show that this equation is true using Leibniz's formula, and then we'll substitute. Now at the start, just looking at this question, you are not going to know that this is the equation you're trying to prove, right? At the start, what you're going to do is just take the original equation and just start differentiating. So we take the original equation and differentiate n times with respect to x. So remember I said I have two products here. So I'm going to have to differentiate each product n times, right? This one minus this one, and it's equal to 0. So let's start with the first one, right? We're going to have to take each of these separately. This is similar to the previous question we looked at, right? So I can let u be this 1 minus x. Now you have to be careful here because it's no longer y, it's y double prime. So v is y double prime. Right? Now, when you're using Leibniz's formula here, this works out similarly to before in this example here, right? We have the exact same u. So from the third term onwards, it's just going to be 0. So it's just the first two terms I have to look at. Alright, now I didn't show the intermediate steps here. I'll leave that for you all to fill in. But in the first term, this first term here, right? Remember the coefficient is 1. That's the first term. We write back u, right? So that gives me the 1 minus x. And we differentiate v n times. Now, this is where you have to be careful. We are differentiating this thing n times, but we already start with a second derivative. So you start with a second derivative and you differentiate n more times, you will get a n plus 2 derivative. Right? So it's the n plus 2 derivative of y, not just the nth derivative. All right, so that is pretty straightforward. Now for the second term, the coefficient will be n. All right, that's where this n comes from. Also, when I differentiate u, I get minus 1. That's where this minus sign comes from. And then when I differentiate this, so not n, we're going to differentiate n minus 1 times now. I'll get the n minus 1 plus 2 gives me n plus 1 derivative. Right? But you don't actually need to work this one out, right? Because once you differentiated this one, then you know, remember the number of times you differentiate and decreases by 1 each time. So whatever this is, just subtract 1 from it. This was n plus 2, subtract 1. Right? And that's the first derivative worked out there. That's all it's going to be. For the second one, this will be much more straightforward. Just bear in mind there's a negative sign here when we substitute in. But for the time being, we can work out this derivative here. We can let u this time be x, right? And this time v is y prime, not y double prime. This time it's going to be y prime. So the first term, again, coefficient is 1. We multiply by u, and we take the nth derivative of v. So the n plus 1 derivative of y. So we get n plus 1 here. All right? And then the coefficient of the second term is n. When I differentiate x, I'll get 1, so it's plus 1. And then we decrease the derivative here by 1, so this is just an nth derivative. Alright, once we have those, we substitute in. Again, remember there's a negative sign here, so it's minus all of this. Alright, and simplify it as much as you can. Now, when you're simplifying it, I find it's useful to look at the derivatives. So there's only one n plus 2 derivative. Right, so that stays by itself. This 1 minus x times this thing stays by itself. There's only one nth derivative. So minus this stays by itself. But there are two n plus 1 derivative. So this one, you can combine it with this one, factor out the minus sign, factor out this n plus 1 derivative, and you get n plus x. Right, so this is how we get this here. And then, well, this is the equation we wanted to show up here that we said we were going to show at the start. But the last thing is to substitute the value for x. So we let x be 0. This just simplifies the derivative at the point 0. This is minus n times this derivative at the point 0. And again, minus n times this derivative at the point 0. Right? Which is what we originally wanted to show. And that's it for Leibniz's formula. Some advice I would give you is, as far as possible, try to practice questions using Leibniz's formula. It is very useful or very helpful, I find, if you do a couple of questions so you get into the habit of how you would write things. That way it comes much more naturally and much easier to you under exam conditions. Right? So when you have to use it in an exam, you're not sitting there trying to figure out, well, okay, what's the coefficient of this thing, or what goes here. You already know naturally, okay, you write down your coefficients, you write down the derivatives of u and then the derivatives of v in reverse direction, and then you go from there. Right? It saves you a lot of time if you can practice it beforehand. Alright, so that's it for this video. It was a bit longer than I expected, but I hope you all now understand Leibniz's formula. Okay, take care, bye.